Welcome to this video. In this video we will be looking at linear least squares regression, and by the end of this video you will be able to fit a linear function to a data set. So linear least squares regression tries to do the following thing. Given a set of n data points, and let's call them xi, yi, determine the linear function f of x equal to a1x plus a naught that best fits the data points xi, yi. So when we talk about how that best fits data points, we have to define some measure of what we mean by a good fit. So how do we measure how good a fit is? Well, if there are only two data points, the problem is pretty straightforward because a line will go directly through just two data points. So there will be no error in that case. But if we have more than 2 points, 2 data points, then unless they all happen to be on the same line, we cannot put a single line through all of these data points. Okay? So we have to come up with a measure of a definition of an error. Right? And then we'll try to minimize this error of the fit. So let's define the residual of the data point I for xi, yi. So the residual of the data point xi, yi is just the difference between the data point yi minus my linear function into which I plug in the data point xi. So it's kind of the difference between the predicted value from my linear function and the actual value yi. So here's a graph from the book on this, right? If I have these different data points, I can at every point evaluate what my function would be, plugging in x1, x2, x3 into my linear function. And then the residual is just the measured value y minus what my line predicts at that location. Okay, so that is the definition of the residual. Now, how can I use this residual to define a total error that I then try to minimize? So the first idea could be that, well, we got a residual value, right, at every point. Why don't we just sum these residual values up? That will give me a total error E. Right, so if I do this, the residual is the function, the measured value yi minus the function evaluated at xi. So the function is linear, so minus a1 xi minus a naught. Okay, so that would be a scenario like this, for example, here on the right. And if you look at this scenario over there on the right, you'll realize that even this line that visually doesn't look like it's the best fit to the data would have an error of 0, right? Why? Because in this definition of the error, positive residuals will cancel negative values of the residual. So we would have error cancellation. So this type of definition for the error is not that great of an idea. What else can we do to get rid of the error cancellation? Well, we could fix this by not taking the residual with a sign, but by taking the absolute value of the residuals, right? That would get certainly rid of error cancellation. So I'm just going to define the error as the absolute value of all of these residuals at the individual data points. So that avoids the error cancellation problem, but it introduces a second issue, namely that for a given data set, there exists more than one function that has the same total error. And here shown on the right is one of these examples here. If you can try to visually keep these apart here, you'll see that both of these lines here have actually the same error if it's defined as just the absolute value, the sum of the absolute values of the residual. So that doesn't really work either, but this idea of getting rid of the sign was necessary, right, to avoid error cancellation. So how else can we get rid of the sign? Well, the other way we can get rid of the sign is by squaring the residual values. So let's define the error as the sum of the squares of the residuals. So if I use the definition of the residual, that would be the sum over all data values from 1 to n of the measured value yi minus the value predicted using xi predicted from the linear function. Okay. Now, in this case, fortunately, for a given error value, the linear function will be unique, which means we can solve this once we try to optimize the error. Basically, we try to minimize the error. Okay, so how do we do this? Or what is this called? It's called linear least squares regression. So what we're trying to do is we are trying to find a0 and a1 in this linear form, where a1 is the slope and a0 would be the intercept, such that this definition of the error, the sum of the residual squares, is a minimum. Okay, how do we find a minimum? Well, E is nonlinear, right? And how do we find a minimum of a function? Well, a minimum is where the partial derivatives are 0. So we take the partial derivative of the error with respect to a0, and the partial derivative is, if we take this definition of the error, the partial derivative is just -2 times the sum of yi minus a1 times xi minus a0. Right, it's just the outer derivative is 2 times the parenthesis times the inner derivative. That would be -1. And that has to be equal to 0, right? We set that derivative equal to 0. That's where an extremum would be, either a maximum or a minimum. And in our case, it will fortunately be a minimum. And then the second condition is that the partial derivative of the error with respect to the second variable, a1, has to be equal to 0 as well. So let's take the partial derivative with respect to a1 of this definition up here. So that would be equal to outer derivative 2 times the sum of yi minus a1 xi minus a0, and then the inner derivative is minus xi. Okay, so that has to be equal to 0. Okay, now these are two equations that we have to solve, and fortunately these two equations now are linear with respect to the unknowns that I'm trying to solve for, a0 and a1. So let's simplify these equations. I can divide the first one by -2, and the second one I can divide through by -2 as well. And let me now apply the sum operator to the parentheses. So the sum applied to the a0 term. a0 is one value, but I'm summing this n times. So that would be n times a0. And I'm going to divide by the -1. So n times a0. Then I have the sum of a1 times xi. Right? So there I can pull the a1 out of the sum. So I have the sum of all the xi values times a1. And that is equal to, on the right-hand side, I have the sum of all the y values. That's the first equation. The second equation, I just do similarly. I apply the sum operator to each one of the terms in the parentheses. So I first get the sum of all the x values times a0. And then the second term has xi times xi. So it's the sum over xi squared times a1. So the sum of all the xi squared values times a1 is equal to, on the right-hand side, I have the sum of the x multiplying the y values. The sum from 1 to n of yi times xi. Okay, so that's a system of linear equations. And let's define some shorthands for this. Let me call the sum of all the x values just s sub x. The sum of all the y values s sub y. The sum of all the x squared values sxx. And the sum of the x times y values s sub xy. Okay, so then with these shorthands, this equation looks like n times a0 plus Sx times A1 is equal to Sy. And the second equation is Sx times A0 plus Sxx times A1 is equal to Sxy. Okay, so that's not very compact two linear equations now that I can solve using, for example, Cramer's rule. So with Cramer's rule, I can directly write that A0 is going to be equal to Sxx times Sy minus Sxy times Xx divided by n times Sxx minus Xx squared. Mouthful. And A1 is the shown ratio over here. Okay, so that's directly the solution using Cramer's rule. So let's do an example. Let's find the linear least squares regression, the line, that fits the data given in the table here best. So we could start out by just graphing this data first, y versus x, and you'll see that those 4 data points, they don't actually lie on a single line. So we're tasked with finding that line that best fits this data, that minimizes the squares of the residuals. So let's dive into this, right? We have the linear function a0 plus a1 times x. So we want to calculate the a0 and the a1 from the linear function. And in order to do this, I have to evaluate all of these sum terms over here. So let's start with that. Let's start with Sx is equal to the sum of all the x values. Sum of all the x values, these are my x values. Sum of all the y values for Sy, those are the y values. But let's start with Sx. Sum them all up. So 2 plus 5 plus 6 plus 8. 7, 15, 21. Next up, Sy. Sum of all the y values. 7 plus 8 plus 10 plus 11. 15, 25, 36. Next up, sum of all the x values squared. So Sxx is equal to sum of all the x values squared. So 2 squared plus 5 squared plus 6 squared plus 8 squared. So that's 4 plus 25 plus 36 plus 64. 36, 64 is 100. That would be 129. And then finally, Sxy is the sum of all the x times y values. It would be 2 times 7 plus 5 times 8 plus 6 times 10 plus 8 times 11. So that is 14 plus 40 plus 60 plus 88. And that's equal to 100, 202. Okay, so those are all of these individual sums. And now all that's left to do is plug these values into the formulas for A0 and A1. So let's do this. So A0 is equal to, and just let me color these in so you can see where these values come from. So let's start with Sx. That's 21. I will need this value here and here. Okay. Then I have Sy. That is 36. That value will be needed over here and here. Then I need the value of Sxx. That's here and here. That Sxx is 129. And then I will have the value Sxy. That's the 202. 202 is over here. And there's one more Sxx and one more Sxy. Which leaves the n. Right? The n is the only value here. And n is the number of data points. So n is the number of points. Data points. So that is 1, 2, 3, 4. n is equal to 4. Okay, let's plug the values in. Sxx is 129 times Sy 36 minus Sxy, that's 202, times Sx, which is 21. And this entire thing has to be divided by n, which is 4, times Sxx, that's 129, minus Sx, 21 squared. Okay, and if you do the math on this, you'll find that this would be 402 over 75. Okay, now A1 is equal to n times Sxy, so 4 times Sxy is 202, minus Sx, which is 21, times Sy, which is 36. And then this entire thing is again divided by 4 times 129 minus 21 squared. And if you plug these numbers in, you'll find that this would be 52 divided by 75. Okay, so therefore my linear function that fits this data best would be f of x is equal to 52 over 75 times x plus 402 over 75. That would be the best fit function. Now, I could calculate the error, right? The error of this approximation. What we would have to do is we would have to do the sum from I equal 1 to 4 of the true value. This is the yi minus the function that I just found using plugging in xi and then squaring this. So let me write the first couple of terms out here. So the first term would be the y is 7 minus the function, so 52 over 75 times the x value times 2 plus 402 divided by 75, squaring this, plus second data point, the y value is 8, minus the function evaluated at x equal to 5, 52 over 75 times 5 plus 402 over 75, this entire thing squared, and then the same term here for the third data value plus the similar term here for the fourth data point. If we plug all of these values in, you would get that this error is 0.9866 period. So that's the smallest possible error that we can get using just a line to fit this data. Okay. So that's the function that we just derived. And if I draw this function now into the graph, I would get this red line here. And that's the line that best fits this data set. Couple of notes on coding this when we get to code this in MATLAB. There's a lot of functions, right, that we have to evaluate, a lot of sums that we have to evaluate. And we can evaluate these sums either by using loops, initializing the sum variable, the sx, for example, to 0, and then doing a loop for I equal 1 colon n, and just adding to the sum variable sx the current value of x of I. Or we can, as an alternative, use MATLAB's intrinsic sum function, and I suggest that you do this because it makes your code so much more compact and shorter. So all you need to do is whenever you encounter a sum symbol, you just use the MATLAB function sum, and then in parentheses you put what you want to sum over. And in this case here, we want to sum over the x values, starting at the first index 1, and then colon, the last index is n. And those indices are given in the sum symbol. At the bottom is the starting index, and at the top of the sum symbol is the end index. So in this case, we can code as x is just the sum of x, parentheses 1 colon n. We can do the same thing if the sum is over the product of individual entries in a vector. So let's look at Sxy. So Sxy would be the sum of what? Well, xi times yi. So if we do this in the sum function, we would take the entire vector x from 1 to n, and then we would do a component-wise multiplication, a piecewise multiplication, with the corresponding entry in the vector y going from 1 to n, so 1 colon n. And in MATLAB, to ensure this piecewise multiplication, we just don't write the multiplication symbol, but we have to write a dot, a point, and then the multiplication symbol, telling MATLAB that we have to multiply each individual entry in the vectors together before doing the sum operation. And that's how we would do least squares regression. Thank you for watching.